Today's note topics is direct variation. Direct variation is a kind of linear function in which our y-intercept is equal to 0. You've learned about these before and probably called them proportional functions. So these are two different terms for the same thing. So direct variation means proportional. And these functions look a lot like our normal linear functions. Normal linear functions we write as y equals mx plus b. We call that slope-intercept form. And we've seen some cases where b is 0, meaning that the function goes through the origin on a graph. So we could call that y equals mx. But instead of making it that simple, we give this slope a different term, similar to what we did with arithmetic sequences, where we didn't call it slope or rate of change, we called it a common difference. With direct variation, we have a different vocabulary. So we call the slope a constant of variation, or perhaps even a constant of proportionality. These are all just different terms for what in the end of the day is just a rate of change. So rather than calling it m, we call it k. K standing for constant. I believe that just comes from different languages where constant starts with a k instead of a c. So we write the equation, a linear equation for a direct variation, as y equals k times x. And that's it, because there's no plus anything. So rather than relying on a slope and a y-intercept to determine our equation, like we do for normal linear functions, we just have y equals kx, and it's a sloped function that goes through the origin. So let's look at Desmos real quick so we can make sure we can visualize something where if we had something like y equals, and we had 2x plus 4. This is a linear function, but since the y-intercept is not equal to 0, the function has a y-intercept up here at 0, 4. If we take away the y-intercept and just make it y equals 2x, it now goes through the origin. So we can make any number of lines that are proportional depending on what the slope is. So we could do y equals 1/4, 1/5, whatever I just know. Y equals 1/5 x. So we have a flatter line that goes through the origin. We could make one with a negative slope, although in real-world problems, these are typically going to have positive slopes. So we can think of these as a lot of things we encounter in real life. So if you think about earning money by working a job, that typically is a direct variation. If you work more hours, you make more money. If you pay for an Uber or a taxi to go somewhere, you pay by how much time you're in the car. So if you go and buy hamburgers, the more hamburgers you buy, the more you pay, and the amount you pay is just related to the number of hamburgers you buy. A lot of problems we do with linear functions, we add on some extra thing like a starting fee or an initial value in order to make the function more interesting. But in the real world, a lot of things we encounter are just these direct variations where we start from 0, 0, and then as we get more of a thing, the line goes up. So that's what we're looking at here, is these linear functions that go through the origin like that. All right, so back to notes. So y equals kx is our general format. We can also, if we're thinking about like a table of values, we find k a little more easily than we find m. So let's make a proportional table here. Okay, so let's pretend that our equation is y equals 5x, but we don't know that. That's a secret. So if this is our x and our y, we could have a value like 2 going with 10, and 4 going with 20, and then 5 going with 25, and 8 going with 40, and 10 going with 50, right? So we have a table of values like this, And when we're looking for slope, we have to find change in y over change in x. That's our rise over run. So rise over run. And the reason that's important is rise over run works anywhere within a graph. So if you think about, let's go back to Desmos for just a second. If you think about any of these lines, or even the line y equals 2x plus 5, these two lines are parallel. So if I pick any spot on the purple line and I check the rise and the run over a certain distance, I'm going to get the same slope everywhere on this line, no matter where I pick. But I need to find a change in y and change in x to make that triangle, basically. But with a direct variation, it's actually a bit simpler because we don't need the change in y and the change in x. We just need to know a y value and an x value. So you could think of it as taking any point and always being able to go back to 0, 0. So rise and run, we said in a slope formula, is y2 minus y1 over x2 minus x1. So if we know that our function goes through the origin, we could just make y1, x1 0, 0 every time. So then we would have y2 minus 0 over x2 minus 0, and, well, we don't need to keep the zeros, so it's just y over x. So in a direct variation, we don't actually care about, it's not as complicated. We don't have to do a slope by doing change in y and change in x. We can just pick any y value and any x value and divide them directly. Remember, this only works if we know it's a direct variation. So here, instead of doing the change in y is 10 and the change in x is 2, like we normally do for slope, we don't need to do that. We're going to instead erase that and just look only within one single xy pair. So one point, and we're going to do 10 over 2 equals 5. Then if we go to another point over here, I want to pick a different color. So if we go to this point here, and we do 20 over 4, we get 5 again. Then if we do 25 over 5, we get 5. So every single xy pair gives us the same thing when we divide it. Unlike a linear function, so just to compare, if we had a list of xy values where there was a y-intercept, so let's do xy, and our function here is going to be y equals 2x plus 4. Again, we don't know that, it's secret, but we're going to use it to fill in these values. So let's say we had 1, 6, and 3, 10, and 4, 12, and 8, 20. So if we just try to divide y over x here, if I do 6 divided by 1, I get 6. 10 divided by 3 is 10 thirds. 12 divided by 4 is 3. 20 divided by 8 is 5 halves? Yeah, something like that. So notice that we get a different number every time, and that's because of this right here is offsetting the function. It's making it so that we can't just go through 0, 0 every time. We need a change in y and change in x to find slope. So m needs change in y and change in x. K just needs any y and x. So simpler to find. Just don't try to use the simpler version if it's a different number every time. So this second one shows us how we can also, a way to recognize direct variation from a table. So if we go through our table and we do like we did in the upper one, and we do 10 over 2 is 5, 20 over 4 is 5, 25 over 5 is 5. And if we find that we keep getting the same value, that tells us that even though 0, 0 isn't part of my table, I know that it's a direct variation because I'm getting the same result every time by dividing y over x. So that's an overview. Hopefully this is a recap as well with proportional relationships that you've learned about before. But our key points are the constant of proportionality, k, and how to find it, and the fact that we only need a y and x value because, like we did over here, we're counting 0, 0 as one of our 2 points, so that we really don't need 2 points. We just need a point to find that k value. And remember, don't do that if there might be a y-intercept. We need to do change in y and change in x. And as a final note, if you did change in y and change in x, it would still work with a direct variation as well. So if I did go from 10 to 20, that's plus 10, and 2 to 4 is plus 2. So then I would do 10 over 2, and I would get 5 as well. So you can do change in y and change in x, you just don't have to do it for a direct variation. And remember that if you're looking at a graph, our way we're recognizing that is by the graph going through the origin. The y-intercept is at 0, 0. And in an equation, we see that there's no y-intercept given. It's just y equals something x. We don't have a plus or minus b value.